Yeah, this is supposed to be ratio. So I'm usually not one for memorizing patterns, but that is definitely a pattern to knock these out. Of course, the one you guys see, the 1.25 grams came from the problem. Okay, so that is definitely how you can work. Think of working these out. Any questions about that? And then the other problem, no one said anything yet, but the other thing I run into, since we have, what, 4 terms kind of strung up together, it looks like you guys are okay. Just keep in mind that basically we're taking all of the stuff in the top times each other, okay? And ultimately, however we're going to do it, we need to divide by everything that's in the bottom. So, looks like we're doing okay that way. All right. So go back in your notes and find this one. And we're going to do a similar thing. Okay, like I said, so this will be for your extra 10 points. So there'll be 20 extra credit points. Okay. And so what I'd like to do is to kind of show you the solution for the first one. And I'm going to turn you loose on the second one. But notice, and actually your homework is like this. If you look at the first one, there's actually 2 problems. There's a 1A and a 1B. Okay, so if I was going to kind of put underneath that is a balanced equation, by the way. If I was going to put under the balanced equation kind of what this is after, okay, it says what mass of each reactant. Sometimes story problems or chemistry problems, I have to concentrate. I'm like, what do they mean, what mass of each reactant? Well, I know the reactants are on the other side, okay? So actually there's 3 parts, not just 2 parts, isn't there? So what mass of each reactant, question mark grams, right? Question mark grams, okay, question mark grams. And I could call this, you know, A, B, and C. Okay, so yeah, I do have 3 problems there. What mass of each, no, that's not right. Those are products. Somebody stop me. You guys are going to let me go with that, weren't you? Okay.
Products are the second one.
Yeah. Okay. What mass of each reactant? Yes, the products are the second one. There we go. Question mark grams, question mark grams. I thought there were just 2. I'll call this A and B. Okay. So what mass of each reactant, okay, is involved, and then it goes up to if 0.143 grams of O2 is produced. So in this case, we're doing a stoichiometric calculation where we know the mass of O2, okay, and we're supposed to knock out the mass of the reactants, those 2 reactants. It's kind of like you know that you're going to make 2 batches of brownies, and you're wondering, well, how many eggs did they use? Okay, it's kind of like that. It's very similar. Okay, so we're going to do that one together, and then on the second one, I'll switch colors to blue here. On the second one, what is the mass of the other products? So for the second one, you guys are going to come up with the grams of this, grams of TiF4, based upon that mass of O2 produced, and the grams of Br2, based upon that mass of O2 produced. Okay? You can do this. Again, the first term is going to be the mass of your O2. The next term is going to be the molar mass of your O2. And then we switch gears into a ratio that links O2 to whatever you're trying to get to. And we finish up with the molar mass of that other thing. Okay, so the first one looks like this. Okay. Okay, do you guys have this slide already? Okay, good. This is the molar mass of everything, right? The 3 reactants, or excuse me, the 3 reactants and the 2 products. No, that's not right. But there's the mass of everything there, molar mass of everything. So you'll be referring to that. Okay, so let's do these together. So in all 4 calculations, we're going to start with the mass of the O2 over 1. In all 4 calculations, we're going to use the molar mass of O2. That first molar mass we use is always what I call the flipped version. So in order to get to moles of O2 using the molar mass of O2, we're going to put 1 mole of O2 over that 32.00 grams of O2. Now I bet we're going for the TiO2 first. Okay. So So now we're ready for our ratio, okay? In our ratio, we're going to put units of moles of O2 in the bottom, units of moles of TiO2, units of moles of TiO2 in the top, and then we're going to go back to the balanced equation and throw in the numbers. Okay, so it's going to be 3 moles of TiO2, 3 moles of O2. Okay, so this ratio, you always use the stoichiometric coefficients. So of course now we've gotten from moles of O2 to the moles of what we want the mass of. So now we're ready for our second molar mass, the molar mass of the thing we're trying to get to, and we're going to use the unflipped version. So if you look back a previous slide, you can see the molar mass of TiO2 was 79.87 grams per mole. That's 79.87 grams of TiO2 per 1 mole of TiO2. Then units of moles of TiO2 cancel. Okay, and we're left with units of grams of TiO2, which is exactly where we want to be. So can you see where we've used the starting mass, the molar mass, the ratio, molar mass. So around according to 3 sig figs, we got 0.357 grams of TiO2. So knocking out now the grams of BRF3. Our first 2 terms are going to be the same, and they'll be the same for you when you go to use your problems too. So we use the mass of O2, which was given, 0.143 grams. We use the molar mass of O2, 1 mole of O2 for 32.00 grams of O2 to get to moles of O2, the flipped version of the molar mass. Now we're trying to get to moles of BRF3. So I would put units of moles of BRF3 in the top, units of moles of O2 in the bottom, and then revisit the balanced equation to put the numbers there. So we're going to put a 4 in front of the moles of BRF3. We're going to put a 3 in front of the moles of O2. So your ratio looks like this. So the ratio always comes from the stoichiometric coefficients. So now we've left moles of O2. We're on to moles of what we want to get the mass of. And we can get from moles of BRF3 to grams of BRF3 if we use the unflipped version of the molar mass of BRF3, which if you look back a few slides, or a slide, that was 136.90 grams of BRF3 per 1 mole of BRF3. Again, what I like about my notes is it emphasizes when we came up with the molar masses of those 5 things, the molar masses were all just like we've done molar masses before. It had nothing to do with a balanced chemical equation. Just had to do with the species and the periodic table. So now moles of BRF3 will cancel. Units will. Okay, and we need to round according to 3 significant figures again. So, 3 sig figs is 0.816 grams of BRF3. Whew, okay. For 10 more extra credit points, you have 2 problems then to do. Okay? And like I said, and it's good. So what a stoichiometric calculation is you take anything, any reactant, any product, and you relate it to the amount of any other reactant or product. It just so happens for you guys, for the second one, you are given the mass of the O2, and you're supposed to find the mass of the other 2 products.
Does it matter what order we do them in?
No, it does not. And it's going to be a similar pattern. And your first 2 terms are going to be identical. Why? Because we're starting with the same mass of the same thing. If we weren't, they wouldn't be identical. After going back and forth, right? So this would be actually the next slide, so you kind of had the answers to it. But we talked about a mass balance, the whole idea that what the mass you start with, as long as it's not a nuclear reaction, should be reflected in the mass that you end with. So actually, these do check. If you add up the mass of the reactants, you get 1.173. If you add up the mass of the three products, you get 1.173. Probably, it's magic. Probably on Monday, we're going to talk about the fact that a lot of times you'll do these calculations, and what the mass you think you should get back, you do not get back. And usually it's bias low, and we'll kind of talk about reasons for low yield. Okay, but this is a perfect world. This is what we call dry labbing it. Okay. So let's go ahead and I'm going to pull up 36 and 41, and actually that's kind of how far I want to get today. So the only thing that's going to be due are these, but I will apologize in advance. Even though it looks like two problems, really kind of embedded in these two problems are multiple problems. So let's kind of look at them together. They're good though. It's good practice. It's all good. It looks like this. So 35, most of you went ahead and handed in today. Again, I'm not going to, either way, I'll be fine. But this is due today. Then this is due Monday. Okay, so here's 36. Okay, and you'll kind of see what I mean by the multiple parts. So I'm going to push these hints out there under the Twitter feed. I'm going to save them as a PDF, and you can download them. I know in my other chemistry class, when I share hints like this, a lot of times I print them out so they can kind of have them next to your homework. Okay, but if you read it a few times, it gives you the balanced chemical equation, and it basically says calculate how many grams of each product can be formed. And by my count, products are on the right side, right? I got 3 products. So basically, for each one of these masses, A and B, you have to do 3 stoichiometric calculations. So, for instance, in the first case, you were given grams of HCl. Well, the pattern we talked about was if you're trying to get mass of anything, I'm going to pick on NaCl first, you have to go from grams to moles of HCl. You're going to have to show calculating its molar mass. Now, that's the sort of calculation you only have to do once. Okay? Then that will get you to moles of HCl. Then you're going to insert the stoichiometric ratio. I went ahead and kind of showed you what you guys have been doing. Okay, if we're trying to get to NaCl, we'll put moles of NaCl. If we're trying to get from HCl, we'll put moles of HCl. Those 2's, of course, came from the balanced equation. Okay, that will get you to moles of NaCl. And then we need to use the molar mass of NaCl to get to grams of NaCl. So that would be the first of 3 for part A. Okay. The second one, if we just kind of going from left to right, trying to get to ultimately the mass of H2O, this is how you would do it. Okay. All of these are starting with that 10.8 grams of HCl. And then the third one for A looks like this, where we're trying to get to that 4th product, the mass of CO2. Okay, but it's got a very similar pattern. And then just to kind of tell you what B is, okay, so B is where, again, 3 problems. You're going from, in this case, 10.8 grams of NaCl3 to both mass of NaCl, mass of H2O, mass of CO2. So there's 3 problems. And I know up there kind of in green I put the small, but you know there's more between. You have to go from grams to moles, moles to moles, moles to grams, basically. Okay. The second of 2 problems looks like this, where actually there are just 2 problems embedded in it. They give the balanced chemical equation, okay, and they said, suppose you want to dissolve 22.5 grams of solid aluminum, okay, and then the first problem is what mass of H2O, how many grams of H2O do you need? So basically for problem A, that first question, we're going from grams of aluminum, 22.5 grams of aluminum, to grams of H2SO4. You guys are going to be doing these in your sleep. So I went ahead and kind of diagrammed it like, we've been doing. Molar mass, ratio, molar mass. The first molar mass is flipped. Ratio is from the stoichiometric coefficients. The last molar mass is not flipped. And then the second one says, Again, based upon that mass of aluminum, what mass of H2 would be produced? Okay, so, wow, it looks like, and this is kind of like the problems we did today, that the first two terms are gonna be the same, aren't they? For both of those. Okay, but the ratio's gonna be different, and then the molar mass of the thing we're trying to get to. So like I said, I'll push those out under Twitter. Any questions? I think that's it. Okay, so have a good weekend, and we'll pick up from there on Monday.